The work is devoted to the study of the zirconium-1 niobium alloy in coarse-grained and ultrafine-grained states under laser-induced shockwave loading. This material is of interest due to the application for the manufacture of shells for fuel elements of nuclear reactors. The shockwave loading was carried out using a high-energy nanosecond laser. A shockwave generated by a laser pulse that creates compressive stresses travels through the test sample material and is reflected from the rear surface. The velocity of the rear surface of the specimen was measured using a VISAR. An example of the constructed profile is shown in figure. These profiles were used to calculate the mechanical characteristics of materials, dynamic elastic limit and Spall strength. Structural studies have shown two possible scenarios: the appearance of internal damage and its absence. Internal damage is of different sizes and morphology. Perhaps this is due to different structural states. A model based on the statistical theory of defects is applied to simulate the damage-failure transition under laser shock loading. The problem was solved numerically for axisymmetric case by the finite element method. Shockwave loading, which is a consequence of laser exposure, was simulated by setting a triangular pressure pulse. Examples of calculations with different thicknesses and amplitudes of the pressure pulse are shown in the figure. The physical and mechanical characteristics of the zirconium-1 niobium alloy in the coarse-grained and ultrafine-grained states under shockwave loading have been obtained. It is shown that the dynamic elastic limit and Spall strength in the coarse-grained state are higher. Thus the material in the ultrafine-grained state is more susceptible to Spall fracture, including laser shock peening. Approximate amplitudes of the loading pulse generated by the laser action are established by means of numerical simulation. The conditions under which Spall fracture will occur have been identified.